Yeah, good evening to all. Now we will see the second topic in the magnetostatic fields. In this topic, we just see the current distributions which are present in the static magnetic fields. The current distribution are categorized in terms of the line current, surface current, and volume current. In in line current, we just write like capital I, and in the surface current, we write like capital K. And the volume current we just write like capital J, right? And now here, when we see the differential magnetic field for the different current distribution, the surface current and the volume current, we define the differential magnetic field for the particular three elements by using the Biot-Savart's law. Now, in the equation 3.6, this is the Biot-Savart's law, where the differential, that is the magnetic field for a particular length of line, can be calculated, where H is equal to integral over line ideal curl AR cap by 4 pi r square. This is the magnetic field due to the line current, and similarly the magnetic field due to the surface current is integral over surface K ds curl AR by 4 pi r square, and the magnetic field due to the volume is integral over volume IdV curl AR cap whole by 4 pi r square. So these are the formulas in terms of the various three current distributions by using the Biot-Savart's law. Next, we go with a derivative part where we find the magnetic field intensity due to a finite and infinite wire. Now here, to determine the magnetic field due to a straight current carrying filamentary conductor of finite length AB. So here we assume that the conductor of length AB is along the z-axis with its upper and lower ends as shown in the figure. So the point A and point B are kept in such a way that the point A is at the bottom and B is pointing towards the top, and it is along the z-axis. Now we are interested to find out the magnetic field due to this particular finite line of length, finite filamentary conductor of length AB. So here, how we have to derive is that if we want to calculate the magnetic field at a particular point P, so we take a particular point P as the point of observation away from the line. Then after taking this point, we just draw a, what we do is that this is the point at which the magnetic field is calculated, and it will be into the page. Now we just draw this point P, and this is it is like an into mark with a circle. Then, as we have learned in the Biot-Savart's law, we take a differential current element on the line as dl, and we take that particular point, and from the point dl we just draw a straight line from the point dl to point P, and this is the distance r from the point dl. And let that point is let that particular line joining AB and DL to P makes an angle alpha. Now this is the basic thing first we have to do, and later on to how to calculate is that now we apply the Biot-Savart's law onto it. So when we apply the Biot-Savart's law, we have an equation 3.9 where we apply the Biot-Savart's law. dH equal to ideal curl AR by 4 pi r square, and we just remove that AR with the formula by R bar by modulus of R. So the differential magnetic field dH is equal to ideal curl R bar by 4 pi r cube. Now here the value of DL and R bar has to be calculated. Now, before going to calculate that, we just have some other for values so that we can just do this in a simple way. Now here, we just, from the point of observation P, we try to draw a perpendicular to the line joining the z-axis AB. So here we just draw a perpendicular to the line joining AP, and when we draw a perpendicular from the point P to the line joining AB, so let that point be like as O, maybe at an origin, right? It is an assumption that, so it is at a point O where it is like 0 comma 0 comma 0, and it makes an angle 90 degrees with respect to the line joining AB. Now this is very important that, so we have to draw a we have to draw a perpendicular from the point of observation to the current element, right? And next, we have to just from the point A, we have to just draw a straight line from A to P, and the angle made with respect to the line, that is the current element AB, we take like alpha 1, and the angle and then we draw a line from point B to P, and we take an angle alpha 2. So we consider that alpha 2 is the angle made from the point B to P. So we have three angles come into picture, where alpha, which is the point where we have taken for the infinitesimal element, alpha 1 is the point where we have taken for the as an angle at the initial point of the line, and B alpha 2 is the angle made from at the end of the line to the point of observation B. Then here the value of DL. Now here we just substitute the value of DL. I will be remaining the same, the DC current, and DL, we just see that the DL we have taken that the height at which DL we have taken, so like it will be like Z. So if it is Z, so we take that point will be like 0 comma 0 comma Z, okay, and then this particular element is towards the, that is the line is towards the Z axis. So the value of DL we can write like DZ in terms of AZ cap, and R bar. If you can see the R bar is the distance from the infinitesimal element DL to the point of observation P. So let the point of observation P is x comma y comma 0, then we get the R bar like rho A rho cap minus Z A Z cap. Right, it is the difference between the two vectors we take. Okay, so um, then we just calculate now we just substitute so in order to calculate the differential magnetic field, we just substitute this value of dl and r in the above equation. So if we just substitute it, so we get this form where the equation 3.11 comes, where h equal to integral over line, it is as I and right. Now before going to substitute it, we just calculate here like dl curl r bar. So when we calculate dl curl r bar, we get a value like rho dz into a phi cap. A phi cap, that into a picture, and then we just calculate. Now we just substitute this dl curl r bar in equation 3.10. So we get the equation 3.11, right? Then we just calculate, we just substitute z equal to rho cot alpha, then we get dz equal to, that is the differentiation of dz in terms of alpha, we get like dz equal to minus rho put cosecant square alpha d alpha, and we just calculate rho square plus z square whole power 3 by 2 will be minus rho cube cosecant cube alpha. Now we just substitute this terms in 3.11. So we get, and if we just mathematically simplify this, we get an equation where the magnetic field H bar equal to 1 by 4 pi rho cos alpha 2 minus cos alpha 1 in terms of A phi cap. So the magnetic field due to the line AB at a particular point P with an angle extending as alpha 1 and alpha 2 from the initial end. So this is the formula to remember for a line carrying conductor. the magnetic field due to the line carrying conductor, making an angle alpha 1 and alpha 2 at the both ends. Right. Now this is the equation for an finite line of line conductor. Now if we can just extend this as we have two cases here. So when we consider that the conductor is semi-infinite, then the point P, that is, we just see that the point A will be at 0, 0, 0, and the point B will be at 0, 0, infinity. Then we substitute alpha 1 equal to 90 degrees and alpha 2 equal to 0 degrees. Then substituting this alpha 1 equal to 90 degrees and alpha 2 equal to 0 degrees in equation 3.14, we get H bar, that is H bar equal to, that is the magnetic field intensity, H equal to 1 by 4 pi rho in terms of A phi cap. And in the second case, when considering that the conductor is of infinite length, so we have point A is at 0, 0, minus infinity, and the point B will be at 0, 0, infinity. Then the angle made alpha 1 is equal to 180 degrees and alpha 2 is equal to 0 degrees. And if we substitute alpha 1 equal to 180 degrees and alpha 2 equal to 0 degrees, then equation 3.14, we get the magnetic field equation H bar equal to 1 by 2 pi rho in terms of A phi cap for the infinite line conductor. Now this is the method how we calculate the magnetic field intensity due to a finite line and infinite line. And thank you for watching this video, and we will meet in the next video. Thank you.